So firstly, good morning, everyone. Thank you for joining us this webinar. So today we are really excited to have Professor Bang Liu. Bang is an associate professor in the Department of Computer Science and Operations Research at the University of Montreal, Canada. He's an associate member of the MELA, Quebec AI Institute, a member of Institute Cultivar, yeah, forgive me my French pronunciation, at the University of Montreal and a Canada CEFA AI chair. His research focuses on natural language processing, large language models and agents, multimodal and embodied learning, and AI for science, particularly for material science. He has published more than 100 papers and tutorials in the high-level conferences and journals. He has served the area chair of conferences such as NeurIPS, SALR, ACL, and many others, as well as action director of the neural network journals. He has received the Amazon Research Award 2025 and also the 2025 Yunfang Award, the Bright Star and Rising Star, the University of Montreal Research Excellence Award, and the WWW 2023 Best Paper nomination, and the George Walker PhD Thesis Award. So Bang is going to talk about today about the advances and challenges in foundation agents and building the cognitive engine. So Bang, without further ado, I will leave the podium, virtual podium to you.
Yeah, thank you very much, Professor Xin, for your invitation and introduction. So just confirm, you can hear me and see my slides, right?
Yes. Yep.
Okay, yeah. So hello everyone. So I'm quite glad to share our research on AI agents at AIMEDx webinar. So the title, I slightly changed it. It's like building the cognitive engine for foundation agents. So basically in this work, in this presentation, I will first introduce our general framework, what we call the foundation agents. Then I will introduce two relevant research. One is about parametric memory, and another is about reasoning in the latent space, which are both core pillars for building the cognitive part of agentics. So, to start with a very simple question, like what is an AI agent, right? So if you check an AI textbook, for example, the very classical one from Theodore Russell and Peter Nomi, it says that an agent is anything that can be viewed as specific environment through sensors and acting upon that environment through actuators. So if you check that right figure, so it's quite simple. So you have an agent system. So it has some sensors which can receive signals from the external environment, and it goes through some cognitive process, and then it can execute some actions through actuators. And that actions will have impact to the external environment. Then the state of the environment will change, right? Then continue with this loop. You receive new signals, you produce new actions. So the most interesting part is what is the cognitive part? How can we implement that, right? So how do you make intelligent decisions based on the input signals? So let's first recap large language models. So this since 2023, the research passion about large language models is like very hot all around the globe. And you can see those on the right part, there's a very elegant AI agent framework. You can see on top of LMs, you can see that the LM is just the brain part. And you can equip it with some external components like the memory to store the experience, the planning for better reasoning, tools to have more diverse actions, and then tools, based on the tools, you can execute actions. So this is a simple LM agent architecture with from the Dr. Bonilian's blog. So basically, you can see based on the language model's capability, we can turn traditional rule-based domain-specific agents into powerful agents which has natural language fluency, broad reasoning capability, and dynamic adaptability, which can be applied to various environments and tasks. So at the current stage, we are interested in several questions. So first, we want to have a reflection about where are we in AI research today. We have very powerful language models, We have quite impressive reasoning capabilities, but they have limitations in like safety issue, trustworthiness, multimodality, empathy, embodiment, and so on. And then what can be improved, right? So we hope to propose a unified framework for AI agents so that within this framework, we can do deep research on different paths. We hope to improve some core capabilities of AI agents. For example, the lifelong learning capability, complex reasoning, emotional grounding, multimodality, and so on. So basically, we want to have a reflection over the current stage and like to better prepare for the future. So motivated by this, like we conducted a large-scale survey and position paper, which named as "Advances and Challenges in Foundation Agents." This is a collective work in collaboration with about 20 institutes all around the globe. So the survey is updated to version 2, which is freely available on archive. So you can check the paper if you are interested in this topic. Like our perspective is that we want to connecting AI with humans and society. So we want to make a comparison between human brains and machine intelligence so that we can draw insights from the biological brain and identify gaps. We also want to develop human-centered and socially beneficial AI. Instead of replacing human beings, we hope that AI can empower human beings and amplify our creativity. And we want to foster human-AI collaboration, encourage transparency and trustworthiness. So this is a figure in the paper I have mentioned just now. So you can see that here we grossly categorize different key capabilities into 3 levels. Well, the green colored one as L1 well developed, and L2 means partially developed, and L3 means underexplored. So for example, if you check several capabilities like visual perception, object face recognition, language comprehension, so those are well-developed capabilities because like in the past, at least 10 or 20 years, like we have so much research on natural processing and computer vision. So many of the capabilities are already commercially available. So you can reliably use them in real-world products. And there are also many key topics which we consider as partially developed. For example, the planning and reasoning capability, reward learning, attention control, multisensory integration. So many of these topics, like they are very hot. There are so many papers working on it, but we cannot say that those challenges are resolved. We can still keep improving these core pillars for intelligence. And there are also many topics which is underexplored, but they play a key role in biological intelligence. So for example, the emotion processing and learning, the memory mechanism like the working memory, episodic memory, different types of memory systems, and lifelong learning capability, the global workspace theory, and so on. So basically, like those, this is definitely not a complete list, and the categorization of different levels are not like 100% correct because there's no correct or incorrect. It's more a subjective way to like consider these different research topics. But we mainly want to show that there's still so many research work to do. So we still lack a unified framework on AI agents. The current AI agents often built on in ad hoc, fragmented way. Like people are working on different topics, like the learning, planning, reasoning capability, different agentic protocols, reasoning capabilities, reflection mechanism, and so on. And we lack seamless integration of perception, memory, reasoning, and action. Those are many different topics. And human brains integrated yet modular approach serve as an inspiration. So that's why we propose what we call the foundation agents framework. So this is a table of notations, but don't worry, you don't need to remember these notations. So we can directly check this figure. So at a high level, you can see this is consistent with the figure we shown at the beginning, like the figure which represents a very like simple framework of agents. Like you have sensors to perceive signal from the external environment. You need to make decisions about these input signals, and then you will produce actions, and these actions will be executed and impact the environment. So let's go to details, let's check this, what we defined as the agent loop from step 1 until step 6. So as you can see, the step 1 is percept the environment, where you can represent the state of the environment as s of t at time t, right? And this is done by the sensor. You can define this perception function as function p, and you got the observation through it. Well, the function p takes s of t, the current environmental state, and your mental state, mt minus 1, and it will produce observation of t. What does this mean? It means that the observation you received from the external depends on both the external environmental state and your internal mental state. So think about like different people watching the same movie or watching the same scene. They have different feelings about it because they have different characteristics, they have different emotion at the same time, so that they will pay attention to different part of the content, and maybe they will have different interpretations. That's why the observation is not only depends on the external environmental state, but also on the internal state. So what exactly is the internal state, which is what we call the mental state? So basically, like we define what we call the mental state to represent several different components which can capture the essential information inside an agent. So for example, we define several pillars, the what memory, reward, emotion, goal, and so on. And why we select these 5 pillars? If you consider memory, this is the most easy to understand, right? The memory part stores your past experience. And the world model is a compressed internal model, represents the external world and can make predictions about the future. So if you think about it, the memory part and the world model part basically captures the past time and can predict the future. And for reward, emotion, and goal, basically you can consider that the reward helps the agent to learn from any experience. And the goal turns the agent from passive responsive manner into more active, like a goal-driven manner, right? And with or without emotion, determines whether the agent is more human style or not. So that's why we consider these 5 pillars are essential. And we further define what we call the cognition function, the function C, where you take the past mental state, mt minus 1, your past experience, basically your action flow, at minus 1, and a new observation of t. Then you update your mental state to m of t, and you produce your action, a of t. And you can further decompose cognition into 2 parts, the learning part and the reasoning part. If you consider the learning part is more like long-term part, basically it's about updating the agent itself. For example, if it's just a model, you're updating the model weights. If it's an agent, you can update in different manner. For example, updating the model weight, updating the memories, the world model part, reward shaping mechanism, and so on. So we call it a long-term effect because like whenever you update the mental state, it will have impact to the future decision making, right? And for reasoning, it's more about a decision making at the current stage. So it's about make the decision at the current time step. So we can further decompose the cognition function C into learning and reasoning. So learning is given the mental state t minus 1, action at minus 1 and O of t, you produce new mental state m of t. So basically it means you're learning some new thing. And reasoning is about based on the new mental state, which compress all the information from the past and the current. You make decision about the current action to take. So A of t equals to the reasoning function R based on the M of t. And until now, the step 4 is about producing the sort of action. You need to execute the action in the real world to have impact to its external environment, right? So that's why you have the execution function, so which is defined by the actor. So you have a function E, which turns the action into executable form. So for example, if it's just calling an API, it's quite easy to execute. But if it's like something like the continuous control of a robot arm, it's relatively more challenge. then like control calling an external API. And then the loop continues. Like once you execute this action, the environment state will change and you continue this loop. So the previous slide shows the framework we defined for a general agent. And this slide shows what kind of capability we want what we call the foundation agent to have. So basically, we hope that the foundation agent is a fundamental intelligent unit with universal understanding, cognition, and action capability that can operate in any environment and collaborate to form collective intelligence. So basically, there are two core characteristics we want it to have. The first is that it is a general intelligent unit, which means it is not specifically designed for any like narrow task or environment. Instead, we hope that it is a general intelligent unit. And the second is that we hope that they can be composed to form more powerful multi-agent organization or multi-agent systems. Because we think that in comparison to build a single very powerful agent, building a multi-agent system is a more effective and efficient way to solve more complex tasks. So until now, I have presented the framework of foundation agents. Next, I will present two recent research. One is about parametric or generative memory, and another is about reasoning in the latent space. As you can see, both memory and reasoning are core pillars in the foundation agent framework. So let's start from the memory. And this is based on this paper, the R3MEM, Bridging Memory Retention and Retrieval by Reversible Compression, and it's published on ACL this year. So first, large language models are stateless, which means like if you give the language model an input, it will give you an output. And in the next time you give it a new input, it has totally no impression about the previous historical inputs. And if you maybe you will question that like when I talk to a ChatGPT, it seems to remember what I have inputted before, right? Because it's not a pure large language model, it will have some other part, for example, the memory part to store the past experience. So like equipping a language model with memory is a quite natural idea. With a memory, like you can buffer the historical information, you can enable continual dialogue, personalized agents, and long horizon tasks. And how to implement such a memory? There are two different ways, right? One is you store information in an explicit way. So you store it in an external like storage system. For example, you record the original textual information, or you compress them as a vector database, or you represent them by KV cache and so on. So basically, those explicit way to store information has their pros and cons. The pros is they are quite easy to edit and interpret because they are the raw information, right? You can easily change them, but it requires extra latency and storage. So you need to do RAG to retrieve the relevant information, and all this information will be stored outside. So with more and more information, you will need more cost on storage. Another way is an implicit manner or internal manner, which means you're trying to compress those information into the network itself. So store the information in the LM ways. So it also has pros and cons, right? The pros is like the information is there in the ways. So they're always available. There's no latency. When you input a new information, the language model will generate the output without extra RAG. But it's also hard to update and audit. So there's a research domain which is about knowledge editing. So basically, it means you need to detect the relevant knowledge from the latent space of a neural network, and you need to edit the information to correct the wrong information without have impact to existing other information there, which is much harder than edit an item in a database, right? So in our RCMM work, we want to maximize the retention and retrieval, which means that we want to maximize the preserved original information, and also we want to have good performance in retrieve the relevant information when user inputs a query, right? So how to do that? How can we simultaneously maximize retention and retrieval while keeping the external storage minimal? So first, in this work, we're working on the generative memory. What is generative memory? It means that we're trying to compress information into the model itself. And we hope that the model can generate the response based on the internal memory when user puts a new query. So we can compare a generative memory with a retrieval-based memory. So for example, in this figure, the user is trying to learn French. And when he asks those tricky ones again, so you can see this query is quite fuzzy. In a traditional RAG system, maybe you need to do some, for example, query rewriting or interpretation to expand the original query, and then you will do retrieval from a database. And based on it, your model will give you the most relevant piece of information. But for generative memory, it's more like a personal friend level recall. It's like a personal assistant. The model knows about the user the best. So it will recap the information from the model itself and directly generate the response in a more personalized way. So for example, in this manga, we show that on the left, the generative memory will give the user quite intuitive example to show how those verbs are being used. And on the right, the retrieval-based memory will give you some more classical material, for example, some information from a wiki or grammar book and so on. So you can see the generative memory is a friend level recall and the RAG system is kind of a best match. Search is not a best fit help. So how can we train a generative memory which maximize the retention and the retrieval? We have several key ideas. The first idea is that we consider memory as compression and decompression. So consider that you have a long context and you need to remember this long context in your memory. Basically, it means like you need to compress this context into a memory representation. And for retrieval, it's like given some query, it will help you to retrieve and decompress the original information. So this naturally forms a dual task from the long context into compress short memory, and from a short query to decompress the original long context. So since this can be considered as a dual task, we want to utilize the reversible neural network. So if we apply it to memory, we call it the reversible memory network. Basically, it means that one architecture, two directions. So there's existing research about reversible neural network as shown in this figure. So this is a classical research work on this topic. So you can see that from X to Y, if you define some intermediate modules like this f and g, then y is equal to x plus f of g, and x is equal to y minus f of g. So based on those intermediate modules, you can calculate y from x, and you can also recover x from y. But transformer itself is not a reversible network, right? But we can actually adapt a classical transformer into a reversible architecture. So this is based on the reference work 1. So basically it means that you can define some adapter module which acts like the F and G network in the reversible neural network. Then you can do like LoRa style fine-tuning. You fix the original transformer part and only fine-tune these M and G adapter modules so that your network can be transformed from non-reversible original transformer into reversible transformer. The next idea is, okay, we have defined the network architecture. We utilized transformer architecture and we inject adapters so that it can be approximately reversible. So what kind of data to use to train a memory network? So it's not always easy to collect large-scale high-quality data for memory training, but consider our perspective of compression and decompression. Then it's quite easy to synthesize such kind of high-quality data. For example, if you collect a set of high-quality documents, then you can use Oracle language model, for example, GPT-4o, compress it into paragraph level. And for paragraph level, you can summarize it into sentence level summarizations. And for sentences, you can summarize their keywords. So basically, you will have a natural hierarchy from documents to paragraphs to sentences and to keywords. And then you conduct some quality filtering to preserve the most high quality part. So putting all this together, which means that now we have training data, which is synthesized by Oracle language model. And they have a hierarchy of different granularity from documents to paragraphs to sentences and to entities. And we have defined the network architecture, which is a reversible transformer architecture. And we further defined what we call the memory token. So what is a memory token? So if you consider like if you generate short query from long context, you are compressing the information, right? But if you want to recover the original context from short query, you need to preserve the original information. So basically, we use a BERT style design. If you consider BERT, there's a special CLS token, which actually compresses the like sentence pair information at the beginning. And similarly, we can inject such kind of special memory tokens during our generation process. Then those tokens will like summarize the original long information, and so that you can preserve the details while compress it into memories. So to summarize, we have each segment prepends a read token, append write token. So this is for like different directions to from compression to decompression. And the token act as summary vectors, bridging segments, and scale to arbitrary long conversation without semantic drift. So this is because like we have these special tokens so that we can flexibly like adapt to different lengths of inputs. And the training objective is we have the forward compression generation process, we have the backward expansion process, and we have the cycle consistency loss, which means like if you have an input context, you compress it into the short memory, and you further decompress the memory into the recovered context. You can check whether the recovered context is still consistent with the original one. So that's why we have this forward and backward and consistency loss. And the experiments show that the RCMM network achieves shorter performance across different tasks when we submit the paper. And for the retrieval performance, it's also the best compared to zero baselines. And we tested the performance in both in-domain and out-of-domain experimental setting. And we also plug in RCMM as a single memory module into existing agentic framework. So, and we compare with other memory design, such as memory bank and the memory rack. In terms of different metrics, like the contextual coherence, response correctness, retrieval accuracy, and so on, RCMM achieves the best performance. And the elevation study shows that both the hierarchical compression and high-quality pair matters to the final performance, and the virtual token and the backward the reversible network architecture are also key to the final performance. So to summarize, the RCMM frames memory as a reversible compression problem, and the RCMM is an adapter-based reversible transformer with virtual tokens, and we achieved state-of-the-art performance in terms of retention, retrieval, and downstream agentic performance, and it open paths to lighter external storage and tighter model memory coupling. So for the next next work is about a special reasoning paradigm, what we call the system 1.5, which is a way of reasoning in the latent space. Sorry. So as you can see that the title of this paper is System 1.5 Reasoning, Traversal in Language and Latent Space with Dynamic Shortcuts. Maybe you can tell from the title, right? We call it System 1.5. So we definitely want to combine the advantage of System 1 and system 2. So it's kind of a trade-off. So first, what is the problem with current reasoning paradigm? So in many reasoning models, they utilize chain of thought reasoning, right? So COT improves the model reasoning, but it's also inefficient. So there are several observations based on the existing research. The first is that many steps don't actually contribute to solving the question. And the second observation is that models often overthinking, even for simple questions. So for example, like this is an example. You ask an open source language model, what is 2 plus 3? This is a quite simple question, right? But you can see this model tried different solutions, and finally it gives the correct answer with high confidence. But during this process, it tried 5 solutions and consumed more than 900 tokens. So that is the overthinking challenge, and it's not only like on one specific model. It's quite often for many open source models. So the prior approaches, there are different ways. The one way is to improve the language level efficiency, for example, produce faster by fewer or cheaper tokens, or you can reason in the latent space. Basically, in this way, you are just reasoning in the parametric space and you bypass the language constraints. So for reducing token counts, like prior research, like do this in different ways. For example, you can decode shorter outputs via length control, or you can compress the chain of thought data into shorter but more informative trace. You can also reduce the per token compute. For example, you can apply early exit, which means you can calculate less steps on different steps, or you can skip redundant layers. But still, for this prior research, they still decode every token for fluency regardless of whether it helps reasoning. Another way is you bypass the language constraints, which means you skip intermediate language decoding and you only do the reasoning in the latent space, which means you only think silently, you don't output the intermediate reasoning process. You will think for a long time and directly produce the output answer. But the limitation is that they will apply reasoning uniformly, either always fast or always slow, without distinguishing which steps are actually critical. And then we can compare these different methods more intuitively via this figure. So check this top left figure. So this is a typical chain of thought, which means you have an input question represented by the blue block. Then you will produce the reasoning process. So those shallow orange color. And finally, after several steps, you will produce the final answer. And you can see at each step, you will go through all the layers of the transformer. And the top right, which is early exit, so it's almost same as chain of thought. But you can see at different steps, the reasoning depth is different. For example, assume you have 20 layer or 100 layer transformers. Sometimes you will calculate only 10 layers. Sometimes you will calculate 100 layers, depending on whether this step is challenged or not. So that is the strategy of early exit. It will adaptively determine how many layers to go through, depending on the difficulty of each step. And for compressed latent reasoning, so you can see it doesn't produce any intermediate tokens, which means it won't produce the language tokens to show how it reasons about the final answer. It will reason for several steps, then directly output the final answer. And the last, for the bottom right, the extra latent reasoning. Basically, it combines the latent reasoning with chain of thought. So this figure shows our idea, which is quite intuitive. So if we consider the early exit, it means it will adaptively determine whether we should calculate less layers or not. And then after the current step, it will go back to the input layer. But our idea is that if you consider calculating less step layers is a horizontal like is the vertical shortcut. You can also have horizontal shortcut, which means from time step t minus 1 to time step t. You can have a very quick horizontal shortcut. So basically, you can have a simple adapter to project the latent representation at the previous time step to the current time step without going back to the input layer. So basically, if you can reason in such paradigm, which means you are traversal flexibly in the latent space because you can skip the horizontal layers, you can skip the vertical layers. So our goal is dynamically allocate the computation in latent space based on the complexity of each reasoning step. That's why we designed these two dynamic shortcuts. One we call the depth or vertical shortcut, another we call the step or horizontal shortcut. So how can we do this? So if you think about what we're doing right now, basically it means that at each time step, at each layer, you have three different ways for the next step. One way is that, okay, at the current time step, at the current layer, I'm already clear about the output at this time step t minus 1. Then but I don't know about the answer. I still need to reason for more steps. Then we can go horizontally to the next layer. Another case is, okay, I need to reason more about the current step, which means I still need to go from layer L minus 1 to layer L. I need to continue the reasoning step vertically. So this is another case. And the last case is, okay, I already know about the answer. I can produce the answer. So, like we have three different choices at each time step, which means we can train a gating mechanism to decide which flow to go at each time step, right? This is a quite natural idea. So, that's how we determine the training and the inference process. Basically, at each time step, at each layer, you will have a gating mechanism to decide which flow to go through. But there are several challenges. And one is like you don't have the data to train this latent reasoning process. And also you don't know how to align the latent space. So we can directly check this figure to understand the challenge and our solution. So as you can see, we divide the training process into two parts. One is language to latent alignment, another is shortcut learning. So basically the first part means that now we don't need to produce the intermediate reasoning process. We directly produce the answer, right? Then how we can train the model for the intermediate process, right? So basically what we have been or what we have done is we take a pre-trained reasoning model and we will align our latent vector with this teacher model. So in this case, like we are aligning the latent representation of our model with a language model trained by chain-of-thought reasoning. And another challenge is how we decide which step is horizontal shortcut, which step is vertical shortcut, which means which step is easy, which step is hard. So basically, we utilized an existing research work, which is called Atom of Thoughts. The idea is that consider a question answering data. You can decompose the data into a tree structure. Well, for example, if you are solving a complex mathematical problem, you will have different paths of reasoning, and you will see the logical process can be decomposed into some tree structures. And each tree is considered a part of the reasoning process, and the root node can be considered as a key step, and all the leaf nodes within the same tree can be considered as the following steps after this root node. So based on this idea, you can divide the data into different paths Well, this step is a key step, and another step is a following step. So this is the training objective for language latent alignment and shortcut learning. So basically, it is based on the label data and also based on the difference between your latent representation and the teacher model's representation. And this is our result table. So for example, we compare our system 1.5 model with many latent reasoning and also the chain-of-thought reasoning method. So the key observation is that we achieved approximate the same or even better performance compared to original chain-of-thought reasoning data. And you can see for many other latent space reasoning methods, they have worse performance than the CLT data. And also, we have much less step. So usually for this data sets, we only require 2 to 4 steps for on average for each sample, but the original chain-of-thought will require more than 20 to 40 steps. And finally, we achieved a speed up from 10 to 20 or even more than 50 times speed up. So simply speaking, we speed up the reasoning process while maintaining the reasoning performance, right? So this is the main findings. We have superior efficiency in terms of the reasoning model. We have competitive accuracy compared with the original chain of thought, and we have very effective reuse. We reduced many of the intermediate tokens. Another advantage of our method is that we can have some kind of test time control. So if you can consider the vertical shortcut and horizontal shortcut, which means if you have more steps on the reasoning, usually we have better performance rate. And if you calculate more layers, for example, if you have a very deep transformer, so increasing the depth will also give you better performance. So to control how many layers to go through or how many steps to reason, you can have two hyperparameters. One is the threshold value for the gate to determine whether you need to early exit or not. And this threshold value can help you to control how many layers to go through. And another hyperparameter, the lambda step, will control how many reasoning steps to use. So after you have trained your reasoning model, you can easily adjust these two parameters so that you can decide how many reasoning budget to allocate for the model. In this case, if you want to deploy your model in different scenarios, you can pick the hyperparameter without retrain the model. So to conclude, the system 1.5 reasoning dynamically allocates the computation across both model layers and decoding steps, and it enables efficient latent space reasoning with controllable test time trade-off and achieve high accuracy with a lot of speed up. So our next step is in the future, we want to integrate the memory and the reasoning in a unified latent space and build a cognitive engine for broad agent applications. And that's all for today's presentation. Thank you very much.
Thank you, Bang, for the excellent talk. Really appreciate your discussion about the memories and the reasoning framework. It's really exciting. So Bang will try to do the Q&A session. So I would try to read out the questions and hope everyone can hear it. Let's see. So if you have any questions, please just feel free to just write it out in the Q&A session. We'll try to go through them. So before that, maybe Bang, I can throw you a couple of quick questions. One thing you mentioned in the beginning about the multi-agent systems could be more powerful. So what's your sort of opinion between the foundation agents versus the multi-agent systems in terms of reliability and how they communicate through different agent, multi-agent communications. So how do you reconcile these two concepts? One is more like foundation agent, another is more like a, a mix of experts, different agents.
Yeah, this is a very good question. So basically, here when we discuss the foundation agent, we're discussing the framework of a single agent, right? We are focusing on the
Mm-hmm.
internal mental state design and implementation, as well as how they learn and reason through this framework. And when we talk about multi-agent system, we mean that like if an agent is generally applicable for different tasks, they should be able to collaborate with other agents. So basically, in this circumstance, the other agents is also a part of the external environment, right? You can receive the
Mm-hmm.
messages from other agents, and you will reason about those messages. And in terms of, let's say, like if you have different agents provided by different service providers, they may be implemented in different ways. Then in this case, you need to have a way to manage the collaboration, like form effective organizations to solve more complex tasks. And I think this is not only the problem of designing a single agent, but also a problem of design an effective protocol to coordinate
Mm-hmm.
different agents or any other entities. And this is actually another exciting project we're working on, what we call the foundation protocol. So we consider that like by combining a protocol with different intelligent agents, we can maximize the effectiveness of a multi-agent system while ensure the communication and the workflow is secured and safe.
Yeah, I see. So you're more like perceive uh, other agent systems like a environment that providing some sort of a influence on the mental state of their target agent. But I do realize a lot of other people are developing more complicated agent frameworks that sort of have a a really narrowly tuned agent to do some sort of
Yeah.
small
And
loops.
I know that there are many existing multi-agent frameworks. For example, people are designing multi-agent framework for AI coding, right? Or for scientific
Hmm.
scenarios, for example, designing new materials or in a laboratory and so on. So as you can see, most existing works, they are defining some domain or task-specific multi-agent framework, and they have a specific set of roles and a fixed workflow or some constraints on the workflow. But we're emphasizing on the general applicability to different environments and tasks. So that's why we didn't
Hmm.
pose specific constraints. So if your unit agent is like general enough and can perceive different signals, understand the different domain of knowledge, then they can form an effective organization by themselves. That is our hypothesis. But we can also define some protocol framework to ensure that everything is under control and provide some guaranteed security functionality.
I see. I see. That's really nice. So, um, of course, other questions. I have many questions. First, you talk about the memories, memory systems. So, what's a typical, let's say, latency of the new memory system compared to just like the one you mentioned, the implicit encoding approach? Because I do feel like the latency is very critical for enabling different type of mechanism to encode memories.
Yeah, that is a good question. I don't remember the exact number, but as you can see that our memory is a generative latent memory, which means we don't need to do any external rack process, right? We don't need to retrieved from an external database. So like the latency is very low because
Mm-hmm.
it's only forward processing. All the information is compressed in the network itself.
Mm-hmm. Um, Maybe I didn't fully understand the difference compared to just the implicit encoding in the network. Um, so what's the trade-off?
Yeah, the key is like if you consider, for example, let's say if you have an LM-based agent, well, the agent will keep communication with a specific user. Then you can consider all those dialogue history can be some experiential data, and you can use this data to fine-tune the model so that the model
Mm-hmm.
can remember more information. But this is not exactly what we're doing. We're emphasizing on the reasoning and retrieval capability of the model, and we modeling this program as a dual process where you can compress the long context into the compressed memory, and you can decompress the original information from a short query. So that's why we turn an original transformer into a reversible architecture, and we combine with synthesized uh, large-scale data to enhance the capability in compression and decompression. So that's the difference between our RCMM and directly fine-tune a model with any type of memory data. And actually, we compared with this baseline and showed that our model can achieve better performance. That is the experiment we have conducted in the ablation study.
Mm-hmm. Mm-hmm. I see. I see. Thank you. Um, Maybe I will just ask about your um, the second part, reasoning. When you're trying to use like classical chain of thought, trying to align the language model with latent space. So if I understand correctly, so that means the model, your reasoning model based on the latent space will be basically uh, will be more difficult to understand compared to the explicit language-based reasoning process. Is that the case,
Yeah,
or is it still depend on how we really understand the process?
yeah, that's correct. Because like when you do reason in the latent space, you don't produce any intermediate process which tells you how you solve the question step by step. Instead, you're trying to like let the model to have a faster reasoning process. So in this way, like people have demonstrated that you will largely improve the reasoning efficiency. So if you check this table, you can see that like, for example, coconut is one of the very classical reasoning in the latent space method. And you can see all the accuracy is lower than the original chain of thought reasoning, but they have more than 10 or 20 times speed up. So this is a trade-off, right? If you want to have very explainable reasoning process, you still need to produce the reasoning process step by step. But the cost is it will take more time and resource. And if you want to have a faster reasoning process, you can turn the reasoning process into the latent space without producing the intermediate tokens. And maybe by like learning a differentiable reasoning paradigm, you can achieve even better performance, but the cost
Hmm.
is harder to interpret. And you can see in
Hmm.
this figure, there are also methods on the bottom right. It combines the reasoning in the latent space and in the language space. Then you're actually giving more resource to the reasoning model so that it can produce better answer. So yeah,
Hmm.
simply speaking, uh, your hypothesis is right. In the latent space, it's harder to interpret the reasoning process, but the pros is it can speed up the reasoning process.
Hmm. I see. I see. Um, that's great. Um, so I have one question about because we are developing agents, and we are always concerned about the the longer task reliability. And I'm just wondering what's you mentioned the memory and some other tricks. So what would be your thoughts about how to improve the reasoning, the long time reasoning process, with really not like simple task. You can right now it's become more reliable, but it's more
Yeah.
complicated reasoning process. How to make it more reliable in general?
Yeah, that's a very good question. I think like this is actually one of the key challenges in existing agentic systems. I think there are two key challenges. One is like how to reduce the cost because many of the agents will rely on many input tokens, right? This will have a very large cost. Another is how to improve its reliability in long-range reasoning. So, for example, if you're asking the model to like solve a very complex task, which involves maybe more than 100 or even 1,000 steps, I think the key is like you need to have a way to manage the complexity. You need to manage the all the action process. So, for example, in one of our work, which is called a data interpreter, we show how to decompose the task in a hierarchical manner and monitor the status of each intermediate node so that the agent can self data science tasks from scratch. You only provide the data and the task description. It will test different like solutions and give you the final performance. And during this process, you need to have different stages, right? From preparing the features to select the model, to execute the model and test the performance and so on.
Mhm.
This is similar. Like first, you need to manage the complexity. You need to have effective way to decompose complex tasks into simple ones. And second, you need to be robust for intermediate errors. When you detect some incorrect status for some intermediate steps, you need to have effective way to recover from these errors. You cannot assume we will be correct at each step, right? And third is that you need
Mhm.
to have very powerful like tool libraries with more and more high quality tools. Actually, you are kind of delegating the intelligent operations from the main model to expert tools so that the main reasoning process can be more intuitive and simplified, right? So I think by
Mhm.
combining these
Mhm.
different designs, as well as like keep learning from your accumulated memory or experience, your system can be more and more powerful and can better solve more long-range challenging tasks.
Mhm. I see the point. Yeah, yeah, I do agree. I think the reasoning, um, I think reasoning capability is really should be combined with domain tools that can enforce the process. So maybe one last question, Bong. I would let you go. So when do you think the AI agents can predict the like say new materials
Well,
autonomously or semi-autonomously?
I think they already show very promising results for now. My guess is that they should be able to do that like within, I would say, 3 to 5 years.
That's good timeline. Thank you, Bang. I really appreciate your time during this Thanksgiving week. And thank you very much for giving us this really exciting topic. Well, thank you.
Thank you for your invitation. I'm glad to share our research here.
I hope to see you in person next time.
Yeah.
Right.